So in 10.7, what we're going to do is take a look at applications. Most of them deal with the square root because we're essentially doing applications in the two-dimensional world. You can imagine if we go to 3D, then we would be talking about cubed roots and whatnot. But we're going to kind of keep it simple and keep it to just basically the square root. And essentially everything is built on this guy right here, the Pythagorean theorem. So I'm going to approach this. We're not going to prove it. We're just going to use it, talk about what it's used for. But the Pythagorean theorem basically relates the sides of a right triangle. So what we mean by a right triangle is this is a triangle that has a 90-degree angle in it. So drawing a right triangle, usually I'll try to indicate that the right triangle has its true right triangle by giving a little square there. So if you see a missing square that looks like a right triangle, it is a right triangle. That's just me being a little lazy, but I'll try really hard to let you know where those right triangles are at. And so basically we can see that a right triangle, my 90-degree angle, has three sides. It's obviously got three angles, one of them being 90, and we'll call that side A, this side B, and that side C. This side here has a special name. It's called the hypotenuse, and it will always be the side that sits directly opposite of that 90-degree angle. And then the A and the B, it doesn't really matter which one you call A or B. It's going to all be the same in the wash. So a lot of students panic about, where should I put A and B? And you don't have to panic. If you want to put B anywhere, call it the base if you want. And that way it kind of settles that argument. But as far as the theorem is concerned, it doesn't matter who's who, as you'll see here in a moment. So what the theorem basically says is if you have a right triangle, these sides here are related to the hypotenuse in the following way. If I take A and I square it, and I take B and I square it, it's equal to C squared. And that's pretty odd because we're talking about a one-dimensional length, and then the relationship actually involves their squares, which is basically a two-dimensional. And again, I told you we're not going to get into proof, but if we, the proof basically lies in if we took an A by A square here, and a B by B square here, and a C by C square there, the area A squared plus the area B squared will be equivalent to the area C squared. And that's kind of the geometry behind the proof. But like I said, we're not going to go through that proof. I just kind of want to show you how odd it is that a two-dimensional situation relates to a one-dimensional situation with regard to the sides. So that's basically our formula. And as any formula is, what we do is we just plug things in and use it accordingly. So first example then, let's find the remaining side. So when we look at this, I have a side 3 and a side 5, and so the remaining side is basically side C. We don't know what that is. So we're going to use the Pythagorean theorem. Oh, and by the way, the reason why it doesn't matter who A and B is notice that we're adding them. And addition is commutative, so it can go either way. So don't get too stuck on who's A and B. Maybe we just call that B and we call that A if you want to be official. But it doesn't matter who you call what. So if I plug things in, we're going to get 5 squared plus 3 squared equals C squared. And so we're basically now able to solve for that remaining variable. This is 25, 3 squared is 9, and I think we're looking at 34. Okay, so to officially solve for C, since this is a two-dimensional shape, what we're going to do is undo that square. Now, here's something really important. Let me rewrite it this way. What we're going to do is we're going to introduce a square root. I'm the one that introduced that square root in order to do this. This is called the square root property. And as you guys can recall, all numbers have two square roots. There's a principal square root, which is positive, and a negative square root, which is negative. So technically speaking, when I'm the one that introduces the square root there, notice there was no square root in the problem until I decided to put one in and use it. We've automatically introduced a plus minus to the answer. Okay, now of course for this situation we're talking about a length, so the value that makes the most sense is the positive one. But when we start solving equations, that negative root actually might have some ramifications. So that's going to come in a little later in chapter 11, but there's our first sneak peek at the square root property, and it goes all the way back to 10.1 when we learned that a number has two square roots, a positive and a negative one. We're usually talking about the principal one, and of course we're talking about it here because we're talking about a length. Last but not least, what I have to do is make sure that the radical's in simplified form. So when we think about 34, 34 basically breaks down into 17 times 2. So neither one of these are a nice perfect square. So that is basically what our length is for C. So this C is the square root of 34 feet, meters, whatever the case might be. Right now I'm unitless because I'm just using the item. So that's how you use it. So we've got a formula. Like any formula, we plug in the information, we solve, we introduce ourselves to this important property called the square root property, which will keep playing a role. So next problem, when we look at this, there's my 90-degree angle. So this 10 is serving as my hypotenuse, so this is C, and how about we just call that B? So what we're looking for is side A. So my Pythagorean theorem is A squared plus B squared equals C squared. And so essentially we're going to plug what we know in. I don't know what A is. B is 8 and C is 10. Alright, and so what we get is A squared plus 64 equals 100. We subtract 64 from both sides and we get A squared equals 36. Again, to get this A by itself, what I'm going to employ is a square root. Square root property, because we know there's two different square roots of a problem, we've introduced a plus minus. So we technically get plus or minus 6 here. Of course, we want the positive root because we're talking about a length. So in this case, A would be 6. And again, that would be in meters or feet or whatever the lengths would be. So there's your initial application. Again, it's very focused on the Pythagorean theorem. As any theorem, we're going to pull it out of our toolbox, plug in the information that I need, solve what's left, and then we have this new idea of the square root property that we're going to be using pretty consistently. Okay, so how about I shut this down and we'll do some more examples in the next video.